Yeah, thank you all for coming out. I know end of the day is like a little rough. My name is Katie Malone. I'm an R&D data scientist at Civis Analytics, and I've been thinking a lot lately about data quality and how to bring a little bit of order to the cacophony of data sets that we deal with in our work at Civis. It's a truism bordering on a cliche that data is getting bigger, both in size of in volume and in complexity. And it can very easily sort of get to the point where there's more data than you know how to use. And so are there ways that we can bring some order onto that and have scientific ways that we can know which data is going to be most relevant for the kinds of problems that we're trying to solve? So what we do at Civis, just for context, is we do a lot of people-based predictive analytics. The origin of our company was we're a startup that started 3 years ago, and basically the predictive analytics team from the Obama presidential campaign moved back to Chicago and set up a company sort of doing their thing, but now instead of for a presidential campaign as a company. And so what we do is we work with a lot of clients who are interested in bringing some data science into how they interact with their customers or their clients. And so there are a few different aspects of this. The thing that I'm going to be talking about the most is building the data and what's the best data that we can find when we're working with our clients. So I want to start the talk by just saying exactly what it is I mean by data quality and what it is I don't mean by data quality. So when I say that we do predictive modeling and we want to make our predictive models as good as possible, what I don't mean by that is just building a model. I mean something that's a little bit more comprehensive. So usually the first step starts far upstream of building the model. It starts with thinking about what the data is going to be. How are you going to collect it? How are you going to process it? And there are a number of different sources that we have to think about when we're starting an engagement of where the data could be coming from. So very often a client has sets of data that they think are relevant or sets of data that they think aren't relevant, but maybe you could think of reasons why they could be. Civis also does a lot of work in-house to aggregate data sets that come from places like the census or from social media, and so those can be brought to bear if we think that they're relevant to the problem we're trying to solve. And in certain cases, we can actually go out and collect our own data by fielding a survey or running an experiment. So there's a number of different places where the data can come from. Once you get the data under control, then you can start thinking about how you're going to build a model. And for the purposes of this talk, by building a model, I basically just mean supervised classification, machine learning kind of black box. Don't worry about it too much. We usually use random forest, but it doesn't really matter that much. The point is, though, for something like supervised classification, there's lots of literature on all the different ways that you can do it. It's something that we've done 1,000 times at Civis, so we have a pretty good intuition for what's going to work and what's not going to work. And the software that supports it is also really good. And then usually, if you're like me, what you do is you build your model and you realize that it's not as good as you want it to be, and then you have to go back and iterate on it and figure out how to make it better. And there are roughly 2 ways that I can think of, very broadly speaking, that you could do this. One is you can go back to the actual algorithm, and you can add some complexity or some pre-processing. The other thing you can do is you can go back to the data, and you can say, do I need to collect more data? Do I need to clean my data better? Do I need to merge additional data sets? And this is, I think, comparatively more work than working on your model. And often the payoff is pretty uncertain. And so we want to have as much of an idea of what we're getting into when we bite off this piece as possible. But it's a piece that can have really big dividends. So I have kind of 2 coupled hypotheses that are guiding my work here, which is that if you have a really finely tuned and complex model that you're training on top of data that doesn't really capture the information that you're trying to get out of it, it's never going to be that great of a model. But we've also seen cases where if you have a data set that's really nice and that really captures what it is you're interested in modeling, even a simple model can have very, very nice predictive accuracy. So are there ways that we can develop the same intuition for the data sets that we have for the modeling algorithms that we might be using? I think we can. And what I want to talk about is what kind of setup or analysis that would allow us to know which data set might be might give us the best predictive accuracy for a given predictive model we might want to build. And so for a little bit more context and what I mean by the consulting engagements we do and what kind of problems we might be solving, this is a splash screen that shows some of the clients that we work with. And you'll see that there's sometimes each one of these institutions, you can imagine having a different problem that they might want to solve. We're never literally solving the same problem twice, but there's common themes. So you might have Arizona State and College Board. These are both educational institutions that are interested in modeling something like maybe educational outcomes. So if you can figure out on, say, Arizona State what kinds of data really help you model educational outcomes well, then those are probably going to transfer pretty well to your engagement with College Board. And that might be a completely different set of data than what the Gates Foundation is interested in or the American Red Cross. These are both nonprofit institutions who might care more about what kinds of attributes help us predict philanthropic donations or like political activism. And to be a little bit more concrete about the sorts of data that we might bring to bear on this, this is a type of work that goes back to our political roots. We do a lot of political and electoral predictive modeling. So if you're trying to do something like prioritize a competitive district or figure out who you think is winning a presidential election, there are a bunch of different data sets that I could think of that might be relevant for this. And me, my background is in physics. I have no strong priors about which one might be best, but there might be data that campaigns have collected in previous years. There might be polling data that you can get. There might be demographic data. And so when you're trying to build a model about what's going to happen politically, it's not always easy to know a priori which ones of these data sets might be the one that's going to give you the most accurate model. So of these numerous options that are available to us, which are the input data sets that are going to make our predictions as accurate as possible? So here's a really simple framework that I'm going to expand on in the second part of the talk. But here's something that you can do to try to develop this intuition. It's not rocket science. You build a model. Hopefully it's a model of something that you care about, like what are the competitive districts going to be or who's going to donate to a nonprofit. Then you have some metric, like let's say AUC. And that metric will tell you sort of how your model is doing. But you have a little bit of an interpretation problem at this point, because let's say your metric is good and your model looks like it's doing a good job. It's a little bit hard to know how to attribute that. Is that because you've picked a good algorithm? Have you got lucky? Maybe the data set is good. And so one of the ways that you can resolve some of this ambiguity is you kind of run a meta study or even an ensemble, if you want to think of it in a certain way, where you're building many related models. So you try to find a number of different dependent variables that are all kind of moving in the same direction that are giving you different measurements of the same like general underlying trend. And then you want to use the same training data for each of those models when you're building it, because what we're trying to assess here is how good is this data at modeling this trend that I'm interested in. And then you sort of aggregate over all of the metrics. And if you're seeing good performance across the board, then because the one thing that that all of these models share in common is that they were all built on the same training data set, then you can say with some, larger measure of certainty that there's a good match here between the information that's in the data set that I've used for training and the problem that I'm trying to solve with it. So that's a very simple thing, but there's another sort of way that you can think about how to do this assessment that I think is a little bit cooler and more interesting, and it's also not well known outside of sort of quantitative social sciences. And so I want to talk about that in the middle part of my talk. It's called item response theory, and I've kind of subtitled this the best kept secret of quantitative social science. This was another one of the things that I had never heard about when I was in physics, and it doesn't get out of the sort of some of the darker corners of quantitative social sciences as often as it could, but I think it's really cool and really interesting, and that's why I wanted to talk with you about it. And then in the last part of my talk, I'll kind of tie this together with the data quality question. But here's the idea of item response theory. Let me start with a couple of examples. This is a framework that it actually has a long history in education and psychometrics. How many people in this room remember taking the SAT? Okay, so pretty much everyone. So you might not have known this, but you were participating in an IRT study when you took the SAT. The SAT is this standardized test. You take it between high school and college. And what it's trying to do is say, what's the ability, for every student who takes it, what's the ability of this student based on their performance of this test? Political science, they use it in political science for a different type of analysis, but one that's kind of cool. What political scientists are interested in doing is rank ordering every member of Congress on a partisanship scale from very conservative to very liberal. The way that they, the data set that they have available to them to make that assessment is the congressional votes that all of the Congress people are making. And so these are both actually kind of the same problem under the hood. And what these problems are saying is that we think that there's some latent trait. We can't measure it directly, but we think it's there. And that latent trait is the intelligence of the student, or it's the partisanship of the congressperson. We can't access it directly, but we can indirectly access it by watching these examinees perform many measurements. So the measurements are things like answering test questions or making congressional votes. And those measurements are being performed by many examinees. So you have an entire Congress's worth of people, you have an entire country's worth of 12th graders. And if you're interested in getting kind of serious about IRT, I just wanted to add that most of the formalism in the next few slides comes from this Baker and Kim IRT book. It's excellent if you want to get kind of serious about this. So IRT has kind of two sides to it. I'll start with the first one, which is we want to understand, it's called the examinee-level analysis. And here's the problem that sort of the textbook problem. So we have a student, his name is John, and he's taking the SAT. And we think that John has some latent ability or some latent intelligence. We call it theta, and we don't know what that is, but that's what we want to measure. But what we do have is the fact that John has taken a test, and that's sort of like the data set that I have in the top there. So for each one of these questions in the test, I have some idea of how difficult it is, where sort of the convention I've picked is that the lower numbers of zeta correspond to more difficult questions. And I also know whether John got it correct or not. And so then if I were to take all of this data and I were to plot whether John got this question correct as a function of the difficulty of the question, I would see the data points that are sort of in that plot there, and then I can fit a logistic to the distribution of the data, and what I'm solving for when I fit that logistic is going to be theta. That's going to be John's ability. So I'm actually solving here for what I think John's ability or intelligence is. And so just to be like super clear about what that means, let's suppose I have some guess that John has an intelligence of 0.4. This is like normally distributed, so he's smart but not super smart. And so if John has an ability of 0.4, then I can plug that into this logistic equation with the known difficulty of each one of the questions, and I can calculate the probability for each question that he gets it correct with this assumption of his ability. Then I compare those probabilities to the actual vector of correct versus incorrect that I see, and I construct a likelihood function that describes what's the likelihood that I see this vector of responses given my hypothesis about his intelligence. And I can solve that likelihood function or maximize it by a method of my choice, something like maximum likelihood, and then out of that I can get an estimate of theta. So I've solved here now for John's ability based on what I've seen him doing on this test. So that's an examinee-level analysis. But the thing that's cool about IRT is you can also flip it around and you can say, okay, now I have a new question, let's say, that I'm introducing into my test, and I want to know how hard this question is. So now we have a different scenario where we have many different students. Each of them has a different ability that I've measured somehow. And I have the vector that parameterizes whether they get this question correct or not. And I want to know how difficult this question was. And just to make it a little bit more interesting, in my sort of item characteristic curve here, this is again just a logistic equation. But now instead of making it sort of what we call a one-parameter model, it has two parameters now. There's the difficulty of the equation, and there's also a discrimination parameter as well. And the discrimination parameter is kind of like if you want to do it. I just decided to get fancy. You can do it with just difficulty as well. But the idea now is that we're trying to solve for, again, we can sort of, as a function, plot all of the data that we have. Do people get this question correct as a function of the intelligence or the ability of the student? And we solve for lambda and for zeta. And the quick intuition that you have here is that lambda, the discrimination parameter, is kind of the steepness of the turn-on curve, and zeta, the difficulty, is sort of how far left to right it is. So for both of those, I can figure out how hard the question is and how quickly or how efficiently it sort of sorts people into smart or not smart. But usually you're in a scenario where you don't know. So both of those scenarios that I just outlined for you there, you know one of the important pieces of information. You either know how smart the students are or you know how difficult the questions are. But in most of the scenarios, you don't know both of those things at the same time. And so you're kind of having to solve for them simultaneously. But what you do have is usually many students who are taking a test, and the test has many questions. So you have this big matrix out of which you can kind of try to get that information. And this is what a lot of the IRT literature is we have a matrix is set up like this, and how do we solve what we call kind of like the IRT equations to solve for both of these types of parameters simultaneously. So just to give you a quick snapshot of one of the ways that you can do this in the literature, they call it the joint maximum likelihood estimation, or the Bimbaum method in IRT. So now we make a big likelihood function that's a function of all three of those parameters, the student or the examinee level parameters and the item level parameters. And you make three important simplifying assumptions. These make the math easier, but they're not any more than that. The assumptions that you make are that the examinees are independent of each other, that there's no covariation between any examinee and the parameters of any given item, so nobody has like sort of an unfair advantage on a certain item, and that the items are independent of each other. And then you have sort of this iterative method that you can use to solve for both of them at the same time. So you make a starting guess of how smart your examinees are, maybe based on like just what's the raw sum of questions that they get correct. You use that guess as the seed for making an estimate of your item level parameters. So now you have an estimate of the item level parameters, you plug those back into the examinee level equations, and you sort of iterate back and forth between the items and the examinees until you reach convergence. So what does any of this have to do with data quality? So IRT, all of the IRT literature assumes that the examinee is a person. And that's sort of the notion that I want to challenge, and I think it's really interesting if we start challenging that notion. So let's imagine that we have a data set. Now I'm back in my sort of data scientist, with my data scientist hat on. I have this data set that walks in the door, and I'm interested in like building a model with it. And so I take my data set and I throw it into something like a random forest, and I build this predictive model on the basis of this machine learning algorithm. And usually in the course of building this model, I'm going to have some holdout like test validation set or something like this, or I'm doing some cross-validation. So I have a bunch of data where I both have the predictions that I'm getting out of my algorithm, and I have whether the true labels from, because I have this piece of the data set that I've held out for my validation. And so for each one of these predictions that I'm making from my algorithm, I can say whether that prediction was correct or not. And so you can see how we're starting to move into a little bit of an idea of asking sort of questions of the data set and seeing if the data set is kind of answering those questions correctly. So just to be kind of clear about the analogy, the analogy here is that the examinee is the data set is the one who's kind of taking the test. And that test is composed of items where every prediction that comes out of a classifier based on training on top of that data set is one of the test items. And the assumptions, just to be completely clear about what I'm assuming here, is I'm assuming that each data set that I'm testing has a quantifiable latent ability to get predictions correct. So I'm saying I think in each one of these data sets, it has some ability to try to capture something like political behavior or whether people are going to donate to nonprofits or something like that. And I want to quantify how much it can do that. And I'm also saying that each of my predictions has a quantifiable difficulty and maybe discrimination as well, which is kind of intuitive that some predictions are harder to get right than others, and that it's sometimes kind of interesting to know which ones are the ones that you don't seem to get very often and the ones that it seems to always be getting correct. But there are a couple places, like you want to be a little bit careful about just sort of throwing things into an IRT solver naively. The assumptions of the joint maximum likelihood estimation technique are worth thinking about. It assumes that the predictions are independent of each other, which is mostly true because we think we're working with more or less IID data. It also assumes that the data sets are independent of each other, and this is sometimes true. I think this is very case by case, but for us, very often we have data sets that share some columns. And so we have to be a little bit more careful, a lot more careful about making sure that if there are any correlations between your data sets, that those are taken into account when you're actually solving the equations. And it's also going to assume that there's no covariance between any given prediction that you're trying to make and the data set that you're using to predict it. And I think that that's usually correct for the stuff that we're doing anyway. But it's worth just being clear about because I could imagine maybe corner cases where that wouldn't be the case. So you say, okay, I'm interested in sort of constructing a methodology by which I can assess my data sets in this way. So what do I want to do? The first thing that you want is a very flexible and repeatable model building framework. You want to sort of define what your test is going to be. And so what that basically means is having a bunch of dependent variables that you think really capture the thing it is that you're interested in studying, because those are going to be the means by which you assess whether you're doing a good job or not. And then for each one of those dependent variables, we're going to build a bunch of models on each of these data sets. You kind of have to accept that these are not going to be the best models that you can build. So we're building kind of a model building assembly line, and these are not going to be bespoke custom models that are going to be absolutely as perfect as they can be. Again, random forests usually seem to work reasonably well. And then sort of as I alluded to earlier, I think it's really helpful to have multiple related dependent variables so that you don't have any questions about whether you just got lucky with any one dependent variable, but you have several different measurements that are kind of all pointing in the same direction. So you build this assembly line in which you're going to be building all of these models, comparing the predictions of the models to sort of like the true answers, and then building yourself a vector of whether it gets everything for each prediction it's making, whether it gets it correct or not. And you just pass your data sets through that assembly line, building up vector by vector, like prediction by prediction, the matrix of what are all of the test questions that we're answering and which data sets are getting them correct or not. And so sweet, you have your matrix that you can stick into an IRT solver. And then you're like, great, I'm going to go get the IRT solver out of Python. And then you do what I did and you Google it and you realize that you're kind of stuck with R. And then you're like, oh, crap. So if you're really interested in doing IRT, there are some really good libraries that do it in R. Like I said, R has a longer history, or IRT has a longer history in quantitative social sciences, which seems to be more kind of like R land anyway. But part of the reason that I wanted to come give this talk at a Python conference is because, as I'm sort of saying, I think latent trait models in IRT is really cool and has more of an applicability than just within the quantitative social sciences. And so ginning up a little bit of interest in it so that, you know, if and when a library gets built, there's like some excitement around that. But anyway, and then the other thing, like I said, for us, when we're thinking about how to solve these is making sure that we're checking all of the assumptions. In particular, we're handling it correctly if there are relationships between the data sets and or if there are relationships, important correlations between the dependent variables that we want to think about. So you can generalize the joint maximum likelihood estimation technique, the Bimbaum technique, by removing some of those assumptions. It makes the math more complicated, but you want to be sure that you're doing that properly. And if you kind of just naively dump this into an IRT solver, in general, it will make that assumption, so be careful. But then there's also other ways that you can actually solve those equations that I just wanted to make a nod toward. There's whole chapters of books that are written on these, expectation maximization, Bayesian methods, and also thinking about correlations in inputs. Generalized estimating equations can sometimes be useful for that. So these are all things that we're kind of like thinking about right now. But I just wanted to mention them as one of the complications if you're going to try to like do this knowledge transfer from education to data science. And so that kind of wraps up what I wanted to talk about this afternoon. The work that we were doing at Civis, we kind of had the best of intentions, like, oh yeah, this is going to be finished by the summer, and then found that actually building that repeatable model building framework was a little bit more complicated than anticipated. So that happens. So we're still kind of, I think we're finishing building that framework so we can build up the matrix for ourselves, and then we can go and think about IRT proper. But also, like I said, making sure that you have a good understanding of the correlations of the data that you're putting in, and also cultivating sets of dependent variables so they're really capturing the stuff that you think is important to you. But in general, all of that aside, I did want to make the point in this talk that I think that latent trait models like IRT are really cool and they deserve a higher profile. They have this long history and they're well known in sort of people-based data science, but as you saw, there's nothing in the math that requires a person-level analysis. So just to make the analogy completely clear, what I think and what I hope I've sort of lit a little bit of a fire in your head about is that there is or there could be a latent trait called predictive power that we indirectly access via many measurements, which are machine learning predictions that are performed by many examinees, and now the examinees are our data sets. And so with that, I think we've built a means by which we can give our data an entrance exam. Thank you. I think I can. I should be able to share my slides. They're not like online anywhere right now, but I can, and then I can tweet out a link. I have my Twitter handle there, multi-arm bandit. Yeah. Are there any reinforcement learning fans here? Yeah.
That was a great talk and great ideas and clearly explained. So thank you.
Oh, thank you.
Do you have like Jupyter notebooks or something where you've done a little bit of testing?
So we have Jupyter notebooks. To be completely honest, the IRT stuff is in R, because given the choice between writing my own thing in Python and using the good one in R, like I'm still better at using the good one in R. But recognizing, the audience when I'm saying this, I think we're interested in like building an IRT framework for Python, because like I said, I think it's clearly useful if you want to do education and psychometrics. I think it's probably useful beyond that. But yeah, the notebooks right now are still mostly using, well, I guess they're scripts that are in R, not notebooks, but yeah.
Yeah, I mean, a tool would be great, but I was just wondering if you have like preliminary results.
Sure.
And also, could I ask quickly, when you say, just to make sure I'm understanding, like multiple dependent variables, so in your data sets, it's like you have multiple indicators for a class. It's not something as simple as just like classifying a division.
So yeah, so to be like completely clear, like one of the toy data sets that we're using for development is we have a data set that has a bunch of data about whether people buy candy. So we have a bunch of different like kinds of candy that you might buy. So we have, I think this is like a little bit more trivial than like would actually be useful, but you have multiple different measures of whether people are like buying junk food, whether they're buying chocolate, whether they're buying chewing gum, whether they're buying whatever. And so I think of those as we kind of like bundle those together into a thing we call a basket, and then you just like kind of run the basket on a data set. But that's kind of what I mean by related dependent variables. But I think it's a tricky, it can be a little bit tricky sometimes to know where like one basket ends and another one begins.
I know it's still under development at your place, but have you had any sort of success story that you could talk about?
So we're not that I can talk about a whole lot publicly.
Okay.
We're kind of like feeling it out right now, and it's one of the first like more like outward facing ways. So we'll kind of see. I think like I said, most of the work that we've been doing so far is in building a framework that can very quickly like run lots of models in the way that I described, because it takes a little bit of engineering. Like most of these algorithms are not really set up to do exactly what I described to you. But yeah, we're still like, it's kind of, we're taking off the training wheels like in the next couple weeks. So yeah, it'll be interesting.
So what are some, I know you mentioned having intelligence, what are some other examples of latent traits that you've seen? Have you seen any in like maybe financial applications?
Ooh, that's a good question. I mean, like I said, most of the latent trait literature, if you're looking for something like IRT, it's assuming that the examinee is a person. So think of any latent trait that you can have of a person. So it would be like intelligence is one. Kind of like anything that you can think of as a psychologist would be interested in, like conscientiousness or whether you get angry easily, like these sorts of things that you can think of as being like latent traits of people. And then, like I said, there's also sort of these political applications, the ones about like congressional votes, I think have been tried, but it really hasn't crept out of like the, yeah, like it really is just kind of in like this corner of education in a way that I think is kind of weird and too bad. But yeah. Oh, yeah, sorry.
It's all over baseball.
It's all over baseball.
Yes, so like the pitcher's ability to induce fly balls that turn into outs, strikeout ability, walks, lots of baseball analysis. Analysts use latent trait analysis, so they can break those into binomial categories and figure out whether it's a true ability or
That's awesome. I didn't know that. Yeah.
You could even argue that like batting averages
batting average
kind of
definitely.
fall
Yeah.
fall into this, especially when in small samples.
I didn't know that. Yeah.
Crowdsourcing also people use that to like figure out who's actually doing the classifying the images and who's just putting them through to try and get paid.
Anything else? Oh, yeah.
Thanks for the talk. I really enjoyed it. I was wondering if you could talk more about what you use the results of the assessment for. So once you know what data sets are effective and what the predictions are hard,
Yeah.
how do you then use that in your modeling process?
Right. Well, so like I said, it's still kind of like preliminary internal, but the place where we want to go with this is sort of like I said at the beginning, informing decisions about when to invest in data is kind of like the big thing that's on the forefront of our head. And by invest in data, I mean one of several things, like having a sense for each kind of class of problems that we solve, what are typical performances that we're seeing out of our models when we're building them on sort of like the best data sets that we know out of. That'll give us an idea if when we build a new model, if it's far away from kind of like what we're seeing for that pack. That gives us a little bit of an idea of like if we need to go in and like recheck the model, if for some reason like the thing that we're modeling here seems to be significantly different from the overall trend that we think it should be fitting in with. And then as it turns out, like a lot of times going out to get data is a significant financial investment. And so being able to either ourselves or when we're talking with our clients say like, it's worth it to invest in these data sets and not in those data sets can be a really powerful thing because that can be hundreds of thousands of dollars sometimes to collect these really big data sets. So just having like a scientific reason behind us when we walk in and say like, this is where you should invest your time and money because resources aren't infinite. So having like a good idea of when you want to make those investments and when you don't is like one of the big things we're thinking about. Yeah. Okay, thank you very much.